In this video, we're going to talk about how to simplify square root expressions, sort of as a beginning into simplifying other radical expressions. Square roots are probably the ones that are most familiar to you, so we'll start right there. You, I hope, know two of these. So the square root of 25 is 5, and the reason for that is 25 is equal to 5 times 5, right? The square root function is saying what number multiplies with itself to give us this value. So the square root of 36 is 6, precisely because 6 times 6 is 36. The square root of 30 is not a number that we would just know right off the bat, but because 30 is in between 25 and 36, I know the answer to the square root of 30 is going to be in between the answers to the square root of 25 and the square root of 36. It's got to be something in between 5 and 6. I could estimate about where it is, 5.4-ish or so. But remember, these, when it's not a nice whole number, it's going to be a weird irrational mess where the decimal goes on forever without even ever repeating in a nice pattern. So in order to simplify these square roots, we're going to use the prime factorization of numbers. So taking 60 as an example, in order to find the prime factorization, I'm trying to find whole numbers that multiply to 60. And I started with 2 times 30. You could start with 6 times 10, or 3 times 20, or 12 times 5. Whatever you want to start with is perfectly fine. But now we're going to break down these numbers until we get each one to its smallest possible parts. The prime numbers, like 2, 3, 5, 7, 11, those are the building blocks of all the other numbers because they can't be broken down any smaller if you're looking for two positive whole number factors of them. They only have one and themselves. So 2 times 30. 30 I can break up into 3 times 10. 3 is prime, that's nice. And now I'm going to break up 10 into 5 times 2. Those guys are also prime. So I have my prime factorization now. It's kind of customary to write it from smallest to biggest. It's not 100% necessary. You can also write it using an exponent to kind of shorten up that repeated multiplication. So we're going to use this to simplify our radicals. If I was taking now the square root of 60, and before we do that, let's just estimate. I know that 64 is a perfect square. That's equal to 8. So it's going to be a little less than 8. That's my guess. So, square root of 60. I'm going to take those prime factors I had before. 2 times 2 times 3 times 5. And then the square root of 2 times 2. That's saying what number multiplies with itself to give you 2 times 2. Well, it's right there staring at you, right? 2 is the number that multiplies with itself to give you 2 times 2. So that becomes a 2 on the outside of the root, and still left under the root is everything else you had, which is 3 times 5 here. And you can multiply that back to being just one number. There's our square root of 60. So in order to just get comfortable with this, it's good to practice looking for those prime factors and also noticing perfect squares when you see them. If you were in class with me, I'd make you do this 30 times, but as it is, we'll stick with 6. So when I sit down to a number like 45, if I know two numbers that multiply into it, great. I'm going to start with that. So I'm starting with 9 and 5 because I know those. If you started with 3 and 15, also great. If you're not sure, that's okay too. We'll show you how to do with that next. So 5 is a prime. 9 can get broken down into 3 times 3. Those are primes. I'm just putting little blocks because they are the building blocks of all the other numbers. And there's my prime factorization of 45. 72, I know that one's 8 times 9. 9's 3 times 3. 8 is 2 times 4, 2 is a prime. And then I can break 2 into 2 times 2. Now we have 3 2's multiplied together, 2 to the third power, and 2 3's multiplied together. Now 94, I don't know off the top how to multiply to get 94. So So I'm going to just use my calculator to start dividing out prime numbers and see which one, when I divide it, gives me a nice whole number. And in case you don't have these memorized, it is a good idea to write down some of those lower prime numbers that you might end up using a lot, just so you have them nearby and you can kind of refer to them as you go. That's our starting list. There are a lot more, but since this ends in 4, I'm going to divide by 2. When I do that, I get 47. Now, I might not be positive if 47 is a prime, so actually let's keep going up this list. 33 is not prime, 35 is not prime, 37 is, 39 is 13 times 3, so that's not going to work. 41 and 43 are primes. And now 47, I am going to say I think it's a prime, and this is how we would double check it. We would just use our calculator to go back and divide out other primes from it. When we divided by 2 or 3 or 5 or 7 or 11, if any of those gave us a whole number, 47 would be a composite number because that number goes into it. As it is, that does not pan out, so 47 is a prime number. You can also just search for that on the internet. I have a lot of search results that are just, is 129 a prime number? And find out fast that way too. All right, on 42, I know that one. 6 times 7. 7's prime. And 6 can be 2 times 3. So there we go. There's my prime factorization for 42. 26 is 2 times 13. Checking the list, 13 is prime, so we're done. 266. Gosh, who made this problem? That's a 2 times 133. Now I'm not sure what goes into that, so I'm going to start checking. 2 and 3 definitely don't work, neither does 5. Let's try 7. Oh, nice. That one did work. It was 7 times 19. And when I check my list, 19 is a prime, so we're done. That's the prime factorization there. All right, that's just our practice to make sure we feel okay kind of fiddling around using our calculator to find different factors. Now we're going to do the thing we actually want, which is to take these radical expressions, look for perfect squares inside them, and use that to simplify. So 45, remember, we had square root of 3 times 3 times 5, or you might have had that as square root of 9 times 5. Either way, we're going to notice that this is equal to 3. So we've got 3 on the outside, square root of 5 still on the inside. 315. Gosh, 5 goes into that. How many times? 63. Ooh, I know what 63 is. That's a 9 times 7. 7's a prime. 9 is a perfect square. I love that for me. So I'm going to write this guy as 9 times 5 times 7. I know what the square root of 9 is. That's 3. 5 times 7 I can put back as 35. 50 is 2 times 25, and I could break up 25, but why? It's a perfect square. Let's leave it. So that's the same as 25 times 2. Square root of 25 is just 5. This guy's 5 root 2. When I'm at 80, let's see. That's 4 times 20. I like 4. Let's keep it because that's a perfect square. And 20 is 4 times 5. Ooh, another perfect square. So let's write this as 4 times 4 times 5. Now, I have 2 of the same number under the root. That means I can take that number out. So this is just 4 times the square root of 5. Now, if you had broken these all up into their 2's, you would still get to the same answer. So don't fret. You would just have this as 2 times 2 times 2 times 2 times 5. You would know this brought a 2 to the outside and this brought a 2 to the outside. And then you'd have 2 times 2 times root 5, and you'd end up right back where we were. Oh no, 512. Maybe you know why I'm not looking forward to this. I'm going to write out some of our perfect squares quick, okay? 2 times 2 is 4, 3 times 3 is 9, and so on. These are just nice to have because they will come up. And so if you can recognize them when you see them in a problem, it's just going to like make your life easier. It doesn't like make or break you, but they are just helpful numbers to know. So those are some of the first few perfect squares. All right, 512 is gosh, 2 times 256. And if you didn't recognize 512 when I got frustrated with it, maybe you recognize 256. Or let's break that one into 2 times 128 and 128 into 2 times 64. These guys are prime. Aha! I'm going to stop because 64 is a perfect square. Fantastic. So I have square root of 64 times 2 times 2 times 2. Now I know the square root of 64, that's an 8. And then I also have two 2's here, exactly two 2's. So I can bring a 2 out here. Now this guy, though, has to stay. It doesn't have a little pair. So this is going to turn into 16 root 2. And you know, when I was writing out my list of perfect squares, had I written just one more, I would have written 256. And we would have recognized it as 16 squared. Ah well. 363. 3 goes into that how many times? Ooh, 121 times. Ooh, love that number. I'm going to stop because that is 11 squared. It's on my list. So this becomes 11 root 3. So notice in all these answers, a lot of them actually had primes underneath the root at the end. 35 is also in here. It's not a prime number, but there's no perfect square I can take out of it. That's the goal. Take out as much as you can so that what's left under there is only the stuff you couldn't take out. Now, we are living in the real world or in real numbers. So you can't take the square root of a negative if you're living inside real numbers. So this one we would say has no real solutions, and that's true for any time your radicand, the number under that root, is a negative number. Also no real solutions. There's a simple reason for this. If you had two numbers, if you had a number, you multiplied it with itself, really only one number, and that number was positive. A positive times a positive gives you positive. What if that number was negative? Well, a negative times a negative also makes a positive because the negatives cancel each other out. So you can't get a negative at the end by multiplying a number with itself. You would need a positive multiplied with a negative. Or I suppose you would need some other imaginary idea that let you take the square root of a negative. That would be wild.